they know on average you're getting 0 voltage and 0 current. All right, and they know quite well that they cannot charge you for something that they are not providing. What they're providing is actually the power. That's the reason why it's called the power company. All right, so what is power? Oh my God, it's a combination of current and voltage, right? Okay, so what's happened to your current? Your current goes up and down. On average, you're getting 0 current. Your voltage is what drives the current. It does the same thing. It goes up and down. All right. So this is the maximum amount of current, and this is the maximum amount of voltage that you end up getting from the power company. This is your maximum amount of current. This is your maximum amount of voltage. So what happens to the sine of omega t? You multiply it by itself, so it's going to give you a square. All right, guys. When you actually graph this, notice that this is time axis right here, and then this is your sine square wave. This is for your power, and this is your power axis. Okay, so what's your average power? Your average power is going to be right in the middle. So your average power is going to be 1/2 of your maximum power. Ooh, so this is what you end up getting. They charge you for the average power. Your average power is not 0. They're not charging you for the maximum. They're not charging you for the minimum, which is 0, obviously. They charge you for the average. Okay, so notice that your average current is going to be 0. On average, you're getting 0 current. On average, you're getting 0 voltage. But on average, you're getting a tremendous amount of power. Okay, so how do you express the average power in terms of the maximum amount of current and the maximum amount of voltage that you get from a power company? Here's what you do. This is kind of neat, and this is a trick that I want you guys to remember. Okay, guys, 1/2 can be expressed in terms of 1/2. Can be expressed like this. All right, so you can express 1/2 in terms of 1 over square root of 2, 1 over square root of 2. All right, so you can take one of these square root of 2s and place it in front of the maximum current, take the second one, and place it in front of the maximum voltage. And I'm talking about this 1 over 2. All right, and now what do you have? Okay, so the maximum value divided by the square root of 2, maximum amplitude divided by the square root of 2 is known as the root mean square of the current, and the root mean square of the voltage. Okay, so you're not looking at the maximum current that you're paying for, you're looking at the non-zero average of the current that you're paying for. Do you get it? So the question is, when do we use the root mean values? As a general rule, this is probably slightly made up because I'm trying to use as much common sense as possible to make sense out of it. Notice that when your true averages are 0, you have to use a non-zero average, okay, because you're paying for something, despite the fact that on average you're getting 0 current as well as the 0 voltage. So that's when you start to resort to these root mean values. Okay, so every time you get these oscillations within your system, whether you're a mechanical engineer or electrical engineer or chemical engineer, it doesn't matter. If your averages tend towards 0, we have a tendency to move towards the root mean values. All right, so that's when we actually use that. All right, so question. What's the voltage that we get from a socket? How much of a voltage do we get from a socket?
120-ish.
Okay, no, that's perfect. 120. Perfect. All right. The amount of voltage that you get from a socket is 120 volts. In reality, guys, the maximum voltage that we get is 170 volts. All right, so 120 volts that you're looking at from the socket is going to be an RMS value. All right, so that's what we end up getting. Okay, case in point, let's just test that hypothesis. So the RMS value in this case is going to be 120 volts. So if that's the case, what is the maximum value that we get? All right, so the maximum value in this case is going to be the RMS value. All right, so take this and multiply it with 120. Okay, so somebody do this real fast. Tell me what the value is.
Like 169-ish.
Okay, so it's like 170, right? Give and take. All right, so I'm just wiggling it over here. All right, so now that we had a discussion, let's get back. So what would you say the RMS value represent usually? Based upon the discussions that we just had, the RMS values usually represent the non-zero averages. Okay, so that's what so you're dealing with an average value. All right, so it's going to give you a non-zero average value. So the maximum value of the current divided by the square root of 2 is going to give you the RMS value. Okay, I'm just going to add a little bit more to it right here. All right, so the power, you can express it in terms of the maximum values of the current and the voltage, or you can just express them in terms of the RMS values. Okay, so that's it. Once again, the formulas are just summary statements of what we've been discussing so far. Okay, so what else do we have in terms of the lecture notes? Okay, so we got some. The hell, let's talk about them.
Before Tesla, Edison built his own generators, one after another, each more powerful than the last. But then, so had Tesla. And surely as well as Edison, he too built turbines and motors. However, and this was the big difference in the long run, Edison's generators could only illuminate things within the reach of his power plant, while Tesla's AC system could reach beyond the old neighborhood. With an ever-expanding grid of power lines, AC could go from coast to coast and just about everywhere in between.
All right, so we got the AC versus DC.
Obviously, the reason a plant generates electricity is to send power somewhere, to transmit it through power cables into the home, the office, or anywhere else there's a need and a handy socket. But the power is equal to the current times the voltage. Therefore, the same power can be transmitted at high current and low voltage, or low current and high voltage. Which is better? Remember, the power cables...
Okay, guys, which one is better? High voltage, low current, low voltage, high current. I think we had this discussion. This was a test question. Most of you guys got this right.
Have a certain amount of resistance. And the longer the distance, the bigger the resistance, because a cable's resistance is proportional to its length. And of course, passing current through a resistance causes...
Okay, so you got the problem with current. The power is going to dissipate in the form of heating, right? So a lot of the energy is going to be lost or converted to heat.
This is heating, which is equal to current squared times resistance.
A lot of the power is going to be lost.
This is wasted heat.
So, which means that by the time the current gets to the consumer, not much of it is going to be available.
For the power company and the consumer, that means a certain amount of energy won't be available at the other end. Since I is P over V, that heating is P squared R over V squared. So for any given power and resistance, the higher the voltage, the less power lost in transit. In other words, the key to transmitting power efficiently is to transmit it at the highest possible voltage. In a modern electric power grid, energy is routinely transmitted over thousands of kilometers at hundreds of thousands of volts. But no matter how it's used, the recipient wants all those watts to arrive at a safe and handy voltage. And that's possible only if the electric energy can be transformed up to high voltage, which it takes to make the long trip to the consumer, and back down to low voltage for use at the end of the line. That task, raising and lowering voltage, is hard to accomplish with direct current. But with AC, it's comparatively easy.
All right, so let's talk about Edison briefly and jump into the history of it. So you get your power station, you're generating current, and then you send the current up to the consumer. Imagine that your power plant is located over at Niagara Falls, and you guys are the consumer here in Chicago. We are the consumers here in Chicago. So what's the problem with that? The problem with that is the amount of power that's going to get lost. All right, so here's the power that we generate that we will get to express in terms of the amount of current generated at that voltage. All right, so this is the power generated. And then the problem is we end up transferring this through a large distance. And here's the formula that's going to tell us how much of this power is going to be lost, meaning how much of this is going to get converted into heat, how much of it is going to dissipate in the form of heat. And how much of it is going to dissipate in the form of heat is going to depend on the resistance that you will experience. And you know that the resistance is going to be directly related to the length of the wire and inversely proportional to the size of the wire. Okay, now we got problems. Distance between Niagara Falls and Chicago is tremendous, so which means that the resistance is going to be high, and a lot of that power is going to be lost in the form of heat. All right, so which means that by the time the current gets here to Chicago, not much of it is going to be available to run this lecture. You can turn on the lights, it's still going to cost you the same. You're not going to see much of anything except some shadows all over the place. All right, so that was the problem that Edison was facing. So how do you solve this problem? Okay, he wants to use direct current. If you're trying to use direct current, the distance is going to matter. Larger the distance that the current needs to travel, larger the resistance is, and much of that power is going to be lost in the form of heating. Okay, so there are two solutions to this problem. Solution number one, and they have a power plant or power generating station at the corner of each and every single block. Okay, so they thought about this briefly. The problem with that is it's expensive, guys. This is overwhelmingly expensive. So they noticed that this would be it was going to be extremely costly, so that's not going to work. All right, so the second solution is you can make the wires really, really thick. All right, so the thicker the wire is, the smaller the resistance is. Obviously, not much of the power is going to be lost in the form of heating. So how thick the wires need to be for you to be able to actually transfer enough current? These wires need to be as thick as most of the regular commercial buildings, the size of the regular commercial buildings. So you're dealing with wires which are extremely thick. Once again, it's not going to work because it's really, really expensive. So we got problems. You cannot have a power station at the corner of each and every single block, and you cannot make these wires so thick that they're as big as buildings are. Okay, so that's either way, this is not going to work out. So as he was struggling with it, he was lucky enough to have someone working for him that he did not notice. All right, so I'm going to go over the brief history of Tesla versus Edison at this point. All right, so that's my interpretation of it. I like my interpretation because it fits into the way I visualize stuff. It's slightly off, but it's still true enough as far as I know. A lot of people think that Tesla is a space alien, so that's not true. So let's make a correction to that. And just as many people think that he's Russian, he's not. This guy is a Serbian. He was a prodigy. We refer to these kind of people as savants. This guy was gifted in physics and engineering as well as mathematics. Obviously, he was born with the skill sets that most of us work to acquire. Evidently, according to some of the accounts that I read, he would have just visions of the stuff that he applied for. When he was 14 or 15, he had the vision of a power plant that later became the Niagara Falls power generator. And then he would come up with these weird ideas. They would just pop into his head as far as he was concerned, and they would just design this sort of stuff, apply for patents. So he had 800 plus patents under his name. If he had the money, he would build them. If he didn't have the money, he would just have the patents. And a lot of those patents, if you just acquire those patents, they just go over the sort of stuff that he himself supposedly built, and I think half of them were not even built. They would not normally work. He was the only person who was able to get them to work, all right, because a lot of them were untested ideas, in essence. All right, so he would talk about having these visions and get them to work and blah, blah, blah. A lot of people think that this guy also had an engineering degree. He did not. He went to an engineering school in Austria for only 2 years. He was making a living by gambling, evidently, which is really weird and interesting. Eventually, he ended up losing all of his money, and then he needed a job, so he goes to France and starts working for the Edison company. And then he was notified that Edison was struggling with this problem, and all of a sudden, he's got a solution for Edison. The solution is really cheap, something that fits into his back pocket, and less than $1, guys. It's a transformer. Okay, so Tesla is the guy who has the idea of a transformer. He talks to his boss and says, hey, we could solve this problem using alternating current. Okay, we could use a transformer. So what does the transformer do? Transformer transforms current into voltage and voltage into current. That's what a transformer does. All right, it transforms voltage into current, or current into voltage, and voltage back into current. It's a really simple design. It's a very simple idea. So he talks to his boss in Paris, and the guy who doesn't quite know what he's talking about, he says, why don't you go to the United States and talk to the man himself? And next thing you know, Tesla is in the United States, in New Jersey, presenting this idea to Edison. He says, this stuff is easy. The only thing you have to do is use a transformer, a device that he himself invented. So what you need to do is the amount of power that you generate and transfer will have to be the same. So use a transformer. So what does the transformer do? Increase the voltage. And when you increase the voltage, what happens to the current? The current is going to go down. So the power that you generate and the power that you transfer will have to be the same. So what you can do is, before you transfer the power, increase the voltage. That's going to reduce the current automatically. So what happens when you reduce the current? The amount of power that you're losing goes down. In fact, they reduce the current to an extent that there's almost no current in these wires, guys. It's extremely low. And everything is sent in extremely high voltages. These voltages are almost 500,000 volts, guys. All right, so the voltage goes up, the current goes down. The amount of power that you end up losing goes down significantly. And then you get to the consumer. The consumer does not want voltage, they want current. So now what do you have to do? Now you have to reverse the process. All right, now you have to reduce the voltage, increase the current. All right, and for that purpose, you use a transformer. All right, so you got two types of transformers: step-up transformer. Step-up transformer is going to up the voltage, and then you have a step-down transformer. What does the step-down transformer do? It's going to down the voltage. So you reduce the voltage, the current is going to go up. You increase the voltage, the current is going to go down. Step-up transformer is going to up the voltage. Step-down transformer is going to lower the voltage. It's going to turn it into current. That's it. All right, so this was Tesla's idea. How well did that work out? Except the only way this could be executed was using alternating current. Direct current does not work. The alternating current is the only way you can get it to work, and there's a good reason for it, as you will discover.